Hello, everyone, and today we'll be taking a look at Module 11, Entropy, Enthalpy, and Gibbs-free energy. We'll also be taking a look at its importance, the temperature of inversion, some sample problems, and at the very end, some applications. So what is enthalpy and entropy? Enthalpy is the sum of the system's internal energy. This is found by adding the internal energy, U, by the pressure and temperature product of the system, which you can see in this equation here. Entropy is the measure of disorder in that specific system. It represents the amount of energy that is unavailable to do work. I wanted to take a look at entropy more clearly and more specifically because it's a concept that I've personally been a little confused about in the past. I found this a reference to a messy room, room B, and I thought I'd like to share it with you. In terms of the definition of entropy or disorder of the system, I could say that theoretically, the second room has a higher entropy value as it has a higher order of disorganization. I thought this was a really cool way to think about it as it emphasizes the importance of how energy is dispersed in a reaction. Furthermore, I learned about some of the trends associated with increasing and decreasing entropy. For one, entropy increases when a substance is broken down into multiple parts. It also increases as temperature increases due to the increase of kinetic energy, movement, and obviously more reactions occurring. Also, entropy tends to be higher in reactions of liquid states than solid states. When you go to a state where there is more dispersion occurring, so for example, a gas state over a liquid state or a liquid state over a solid state, there will be higher entropy because more reactions are happening as things are able to flow. Lastly, entropy is also increased in reactions in which the total number of product molecules is greater than the total number of reactant molecules. Overall, these trends just allow us to reflect on what entropy is and understand its importance in terms of understanding the reaction fully. So let's take a look at some examples. So please just predict using the trends whether the entropy will increase or decrease. So for our first reaction here, entropy is decreasing because we are going from a state of high dispersion to a state of lower dispersion, from a gas to a liquid. In our second reaction, we know that the entropy is decreasing because we are going from a reaction that has 4 moles, for example, if you were to look at the mole ratio on the reactant side, to 2 moles on the right side. So since we are decreasing moles as we go from reactants to products, we are decreasing the entropy. In our last one, entropy is increasing actually for 2 different reasons. One, because it's turned into a gas, a state of higher dispersion, and also we are, if you were to look at the coefficients for each molecule, we know that the moles are at like a 2-to-1 ratio, if you were to imagine the one here and the one here and the one here. So since the number of moles are in products are more than the moles of the reactants, then we know that the entropy is increasing. Knowing this, we can say that the enthalpy of a reaction alone is not sufficient to determine that a process is spontaneous. We cannot just simply look at the internal energy of the system without considering how the energy is dispersed in that system. As we know from all the trends, entropy represents so many different characteristics of a reaction. We can't just disregard that or we will not find accurate results. If we can use both data sets, however, we can begin to start analyzing things properly. For example, I created a little chart here. Let H represent enthalpy and S represent entropy. And we know here that if enthalpy is under 0 but entropy is above 0, the reaction will be spontaneous at all temperatures. In contrast, if enthalpy is above 0 yet entropy is under 0, we know that non-spontaneous reactions will occur at all temperatures. Please just keep this delta G value in your mind right now. We'll go into a little bit about what that means in a second. What is Gibbs free energy? What is this delta G value? So as we can see here, Gibbs free energy is the change in the enthalpy minus the temperature in Kelvin times the change in entropy. And then here our delta H equation or enthalpy equation is something that we've already looked at before. So we can figure out so many things because of Gibbs free energy. We can figure out a reaction spontaneity, its favor direction, its energy input or output. We can predict so many different things with these different values as Gibbs free energy combines both enthalpy and entropy data sets. If delta G is positive, the reaction is non-spontaneous. But if delta G is negative, then it is spontaneous and favors the products. Knowing this, there must be a temperature of inversion from a non-spontaneous process to a spontaneous process. What is the temperature of inversion? So as we can see here, this is a graph that was taken from our lecture content in Chem 112, and T1 is a very, very important x-coordinate here. As we can see that anything before T1 has a non-spontaneous process occurring. Yeah, anything above T1 has a spontaneous process occurring. So there's a temperature here that is basically the indicator, that is basically the switch, that as soon as a reaction reaches this temperature, it goes to a spontaneous process. And this is this temperature of inversion, it exists for practically, if not all, reactions ever. So how do we calculate the temperature of inversion? So what we did is that we set the Gibbs free energy equation to equals or above 0, and we isolated for T. So we know that the temperature of inversion is equal to the change in enthalpy over the change of entropy. So let's use an example. So here we just did our basic steps. We were given our enthalpy and entropy. We plugged this into our equation, and the delta G value is equal to negative 5,500 joules per mole. Since it's negative right here, we know it's spontaneous and that the reaction will proceed. So just a little reminder of the temperature inversion. Keep that formula stuck in your head. And now let's practice it. So here we divided the enthalpy value, however, we converted it to joules to make sure our units line up, and we divided it by our entropy value, and we found that our temperature is equal to 247.7 Kelvin, which when converted into Celsius to make it more casual, it was negative 25 degrees, which makes sense. So now let's take a look at some applications with this specifically. Let's take a look at some acids and bases. So here, please pause the video and solve this question on your own. So as you can see here, when enthalpy and entropy are provided, we can find the Gibbs free energy. Analyzing this reaction, we see that the value is negative, indicating that it is also a spontaneous reaction. This makes sense because we are dealing with a very strong acid being hydrochloric acid and a very strong base being sodium hydroxide. Normally, this would undergo a neutralization reaction. So let's take a look at another application, which is concentrations. So here, we can shape the Gibbs free energy into something called the Nernst equation to help us solve questions in non-standard conditions. For example, we can use the reaction quotient Q when dealing with questions with various concentrations. Here, the free energy is equal to the standard state free energy added to the product of the R constant, the absolute temperature, and the natural logarithm of the reaction quotient. If the reaction is in equilibrium, then Q is equal to K, and you could replace that value interchangeably using the concentrations. So let's try some examples. I hope you're still with me. So please pause this tutorial again, solve this. Some tips. The first step is to try to find the Q value using the concentrations, then convert your temperature into Kelvin, and then find the free energy value. So this is what I did. Here we calculated the reaction quotient by dividing the product concentrations by the reactant concentrations. Then we plugged in these values, converted temperature into Kelvin, and then later on in our later steps, we converted all the units to kilojoules per mole. I cannot stress this enough. A thing to ensure when you are calculating Gibbs free energy is that the various components in this equation tend to not always be the same units. Enthalpy is usually in kilojoules, while entropy tends to be in joules. To avoid this mistake, just be on top of it, make sure your units are correct, and convert as needed. So in this specific reaction, since delta G is negative, the reaction is spontaneous and will therefore favor the right reaction and release energy. So taking a look at some more applications, the good thing about Gibbs free energy is that it applies to every single reaction everywhere. So for example, we could calculate the delta G for melting ice. Try to predict to yourselves right now whether this would increase or decrease entropy. From our trends, I predict that the entropy would increase with melting ice due to the transformation to a liquid. You are now going from a solid to a liquid, so a state of lower dispersion to a state of higher dispersion, so the entropy would increase. Also, you can use Gibbs free energy with chemical equilibrium, Q and K, which is what we did. We didn't use K as much, however, you can. And in electrochemistry, you can also use Gibbs free energy in relation to cell voltage, E cell. We didn't go over that in this tutorial, but if you would like to know more, that's in our lecture content. So going more specifically into delta G, we are given the enthalpy and entropy. We plug this into our Gibbs free energy equation. This time we converted our entropy into kilojoules per mole, found that it was negative 0.44 kilojoules per mole, which is spontaneous. This makes sense because we know that ice melts anywhere above 0 degrees, and so since this is at 20 degrees, we know that it will melt spontaneously. I hope this has all made sense and that you've enjoyed this tutorial. Good luck with chemistry. Here are some citations in case you would like to investigate these concepts further. And overall,